Okay, this is our inference operation. So the first step is that we create a rules list, right? So one by one, if there's two rows, then two rules will be instantiated and added to this list or if then rule. And then before inference, we need to set up the condition too, which is similar like what you have done in the rule generation. Okay, but we did not create a rule at all. We simply you need to simply loop through each column. Well, actually, we just have one row. And look through each column, pick up the fuzzy set. This fuzzy set is specified by the user as the condition. Okay. So I'm not going to do that for you, but here I suppose that in the scenario that antecedent will have three fuzzy sets specified. The third, actually, the second one, the zeroth one, and then the first one will be used to specify the rule. But the second one will be used for the condition, try to inference the result. So I kind of hard coded in this way. You should implement your own code to let the user interface complete. We are supposed to let the user specify its condition right here in the condition data grid view. So it's a similar way that you pick up the fuzzy set to compose if-then rule. So you need to do that by yourself. But for this moment, well, I kind of trick. I prepare fuzzy set condition 1, condition 2, like that. And by default, well, it's a trick. By default, the C1 is came out from where? Came out from the tree view main, right? Tree view main. And as you can see, there are two. Well, you need to change the code. Okay, and you need to change the hierarchical or this tree view into three label. You need to do that by yourself. But for current demonstration, we know the zeros first, second. The second node should be the universe, antecedent one universe, right? So I suppose the C1 should come out from the zeros antecedent. Okay, so in this case, well, tree view main, and there should be the nodes 0, 1, second. And the child nodes should be the 0, 1 will be used for the rule specification, and the second one will be used for condition. All right, so it's a kind of trick, tag. All right, and we know it's a fuzzy set, so cast it. Okay, remember that you need to do your correction of the condition by yourself from the data grid view, not what I have done like here. All right, the third one, the last one, the third one, and the output should be in the other way. So, and then since I have C1, C2, so I can, well, I can construct the condition list. So condition clear first. Condition add one after the others. Condition add C sub 2. Okay, so I have condition ready. Then I can inference the given condition. I inference the result for the specified condition, right? All right. So how can we inference that? Since right now you have rules, right? As you can see, all the data has been stored right here. You have rules, you have conditions specified, and you can inference. And remember that in our if-then fuzzy rule, we do provide inference right here. Once you give me condition, I will return the fuzzy set back to you. All right. So the inferences right here should be in this way. So I kind of well, I still use for loop. I need from 1 up to rules, right? It's correction, and the length, the number of items will be put in the count. Since rule is a dynamic list, so for a dynamic list or collection, there is a property called count to show the number of components within this collection object or list object. So I plus, all right? And right now what we can inference is that if we pick up a rule 1, we will have inference function ready for you, right? And basically, after the inference, it will return, well, this one will return a fuzzy set back to you. So we need to use a fuzzy set reference to recover it. So, well, in here, I kind of prepare a fuzzy set. Call it final output. It's a fuzzy set. But as you can see, if you have multiple rules, the output of each rule will be united, right? It will be united by using the union operation. So we have better to bypass this condition. If I exactly equals 0, then final output final output directly equal the result of this inference, right? And inference you need to supply condition. So I just put my condition there. So we simply let each rule inference by itself, and we simply get the output. And if it's not the zeroth rule, then what? We should unite it together. Final result, final output, united with what? With rules, excuse me, with the result of the rules I. Okay, let's run. Output. Alright, so error message is pumped to you because we did not initialize the value. So it's very simple. Just put a none because it's a reference type, so put it on Europe OK. But as you can see, I mean, if you are familiar with the convention of the operator, see, if you have an object binarily operated with another object, and also the result will assign back to the original object, then you can write the code in a shorter way, like this one. It's the same, okay? So even though we did not define this operator, right? We simply define the union operator. It's okay because by default, the compiler will compile this code as final object equal final object united with the right hand side. So you don't need to worry about that. Alright, that should be the final output, right? So usually final output will be the union or two what? To cut it, value cut it fuzzy set. Okay, that's normal, right? So then let's go back to our rule, if-then rule. This is about the time we try to implement our inferences. And for the if-then rule, everything has been specified within the antecedent, right? And also you have a conclusion fuzzy set specified. You need to inference is that user will provide you a conditional list. It's a list of fuzzy set. So you can start inference from this point. And by default, the result, inference result should be what? Should be what? Well, it's very simple. We will prepare a double smallest file string, right? And the result should be what? We will use smallest strings to cut the output. Output fuzzy is right here, conclusion, right? So we don't need to specify this local variable at all. Return smallest file, cut conclusion. But smallest file strings you did not initialize, so let us initialize into 0.0. It's okay. So the problem is that you need to find the correct smallest file strings. So you need to look through each antecedent, right? Compare with the condition and the antecedent fuzzy set. Try to get the intersection of both fuzzy set, and then project to get the maximum degree of the intersected fuzzy set, right? And that will be the firing strength for that antecedent. And if you have multiple antecedents, you need to find the minimized value. So we call smallest firing strength. Initially, we should not set into the zeros. We should set into what? Double that maximum area. That is the beauty of C# programming language, because C# programming is running on a so-called managed platform, and the platform to provide, actually that should be the .NET framework, provide a supporting class for you. So this is a property of double type. All right. So then we will look through each. Well, since it's a comparison, so we have better use for loop int. I start from 0. I smaller than the antecedent, because the antecedent is a list, right? We do not know the length. There is no any property name called length, but instead, if it is the dynamic, well, dynamics list, then we have a count. Count meaning the number of elements right now in this list or in this collection. So I plus. So this is about the time we kind of take advantage of the operator that we just defined, earlier in the class. So we take out the antecedent, the fuzzy set, right? The ith fuzzy set, and then intersect with the condition, the ith fuzzy set, right? So we will have a binary operator fuzzy set generated from this intersect operation, right? Not conclusion, excuse me, condition. Okay. And then, since it's a fuzzy set, we can access the property called maximum degree, right? All right. So this value came out here, and I think we have better have local block variable anyway. Double file rule. Well, anyway, double D. All right, never mind. So D sometimes can be regarded as a similarity between the antecedents and the condition. Well, it's okay. So since we have the, and if D is smaller than the smallest strength, right? Smallest strength will be assigned with D. Okay, probably I'd like to change the name, make it much more meaningful to degree. Okay, that's it. So we kind of look through each antecedent one by one and get the smallest strength, smallest degree to serve as the smallest file strength. So that would be the condition for inference, right? So we get the smallest one, and we use that to cut the output fuzzy set. So inference is just like that. Okay. But as we know, the resulting fuzzy set, usually we use cut operation, right? But sometimes user might prefer using the scale. So we had better that the user specify whether should we use cut or use scale. So currently there are two references, so later on we will make a change. So we kind of like to add a bool. Using cut. Okay. Otherwise, if using cut is true, then definitely we will use cut to get the output fuzzy set. Otherwise, we will use scale. So by default, is using cut. So in this case, we can change our statement into if using cut, then return this binary. Well, actually, it's a unary operate the fuzzy set, but for the C# programming language, it's a binary operation. Else, return smallest strings times conclusion. Right? We do have this one. We don't. It's double conclusion. No, we do not have this one. So we need to go back to our fuzzy set. Overload this operator. Intersection, union, cut. Yeah, we do not have scale. Alright, so I kind of readily prepare a asterisk symbol. Alright, so you need to change that by yourself. We're no longer to use value cut. So last time we do provide a cut value, right? It's cut value. So constructor, you should prepare another constructor for the scale operator somehow. Alright, so it's ready for us right now. We have if then rule, the inference. So if then rule class itself is self-contained. We have the rule has its antecedent right here and the upper right there, and it provides an inference function for us to call it. And later on, we will implement this function because sometimes the people might surprise the condition as the real number. It's called crisp value, right? And the probably user like to have a crisp value out. So, but right now, by default, a fuzzy set is outputted. The result is a fuzzy set. So far, it's okay. So, I think it's about the time we can test our solution. All right, so we start from here. All right, comparison error. Try to debug your code. Right here, the first one. Yeah, because we simply change, right? Previously, we changed the inference, the signature inference. So, well, so this main form. It's main form. So you have better in the form design. Somehow, well, for example, I have a checkbox. I have a checkbox. And I call it CKB cut. By default, it's checked. CHECKED. Check it. Okay, check it. And face text cut. Alright, so it's user interface in the main form. So back to the form. Because this function we're going to need another parameter. So I simply CKB cut. Check it. Right? So user can means arbitrarily means check the checkbox. Alright, so it's almost there. So we can check the functionality of our application. New universe. So remember that these two should be the input universe, right? They should be put one label down of this node. Okay, they should be moved to this input universe. You need to do that by yourself. And only one universe will be specified for the output universe. So remember that. And right now I have a triangular fuzzy set. Oops, excuse me, I need to delete it. Well, system crash. Well, you need to debug it. Later on. Alright, so let me quickly test our code. New universe. The first universe add a fuzzy set. Okay. The second one should be a bell, fuzzy set bell. The third one I like to specialize as a Gaussian. Upper fuzzy set, well, we do not have a trapezoid, right? So you have better add a trapezoid. Trapezoid fuzzy set is usually used, in fuzzy inference modeling. So you need to do that. Bell, I kind of add a bell, and names I add a step down. Alright, so right here. The step down, I like to change a little bit the parameters. Step down, so probably 16, and maybe 32. Okay, and bear function somehow has been scratched. The problem is coming from slope, I think. Okay, so sounds alright. And how about the Gaussian one right here? Gaussian one is right here. Alright, it's not good at all. So how about the bell? Center, move to 16. Width, maybe 5. And then my Gaussian, I will move min to 24. Standard deviation changing to 3. So I can intersect with two antecedent different points. Okay, that's the purpose that I do have. How about triangle F3? And I would like to move to the center, move to the 16. No way. Depth should be smaller than 16. Okay, this is the one. And for the triangle 1, 0.5, center 0.5 minus, how about right? Should be change to the 16. So I kind of intersect with this point. Intersect with, well, the other triangle I might 0, 6, start left, change to 7. Okay, got it. So everything has been specified by the user, right? User defined this universe and universe for his input, and this is output. And then he specified the possible fuzzy defined on the universe. So start from that point, the user can add a so-called equivalent rule. Suppose I have two rules need to specify. The first rule is right here. Quickly the first one. So you need to do the four proof, right? The fuzzy set of universe can only be specified on this column. This column should not be allowed to specify on this column, right? Because the universe are different. So make sure you do have this kind of for proof. Okay, so rule 1, universe 1, rule 1, universe 2, output fuzzy set. So for the rule 2, this place, oops, I should select second one, bell, step down. So make sure your rule selection is legal. Anyway, triangular fuzzy set 2, bell 1, bell 2, bell 3, step down. Okay, seems alright. So about the time we inference the result. So let me set a breakpoint on the inference. Okay, here. Okay, this is our code. So when user click on inference, so the first thing is that we build the list of rule, right? So one row and then the other row. So the first row came out, and then we prepare antecedent parts. The antecedent part originally count is 1, and count is 2, and this is complete. In the conclusion, so conclusion antecedent part, we simply take the tag, convert it. So we have necessary data ready for a rule creation. So rule instantiation right here. And the antecedent part, there are two fuzzy set specified condition also where fuzzy set specified. And it's about the time we create a rule. So once the rule is created, we can add it to the rules list. So initially a rule list is there's no any rule store. So after this time, rules to have count 1 to have one equivalent rule specified. All right, similarly. So let me execute to this time. So rules has 2 rule specified, right? It's okay. Then actually you should do this by yourself. You should get the condition specified by the user from the data grid view, not the one that I cheated right here. Okay, I kind of just take it the second node or the second universe to set C1, C2. So C1, C2. So I kind of prepare conditions at C1, at C2. So up to this point, rules has been specified in the rules list. Condition has been prepared. And it's about the time we ask the doer to inference the result for us. And this is our responsibility because the data is right now specified in the form, right? So form needed to collect the result and united these output files together. Okay, so let us trace the execution line by line. So we are about to let the zeros rule to inference itself, right? And since this is the first time, right? So we execute this line. So right hand side will be executed first. If I press the F11 key, came to here. So take a look at a condition. Count 2, right? 2 party set. So triangle and Gaussian, right? And how about using cut? True. All right. So we are within the if-then rule object. Antecedents is already there. Conclusion, output party set is already there. So the inference is simple. We try to get a filing strength from comparing the antecedent and condition to get a degree of similarity, and then find the minimal degree to serve as the filing strength to cut or to scale the output party set. The inference is so straightforward. Okay, so the first one, degree. Well, since I pressed F, so we will instantiate intersect party set. So it's a binary operator party set. So create it, and then get maximum degree for us. So we get degree. The first degree is 0.27. Well, if you take a look at the chart, can I see it? Tell me I can see it. So this is the first condition, and I cut the right here about probably 0.3, probably 0.3. See 0.28. It's okay. I mean, just came out from the comparison there. So it will be assigned either to the smallest, because smallest right now is the largest value, right? So once we have finished the antecedent zeros antecedents comparison, then we have final degree 0.27, and then the first antecedent try to intersect it, get a maximum degree right here. So create, what's it? And how about degree? 0.5, right? 0.5 does not smaller than the current 0.27. So finally, our smallest filing strength should be 0.28. Use that to cut the opposites. We're not going to dig into the details. So we will have, right now we have file set ready. So we complete the inference right now. So let us continue. Okay, take a look at the file set curve carefully. So what we have done is that, well, we use the this file set as condition, right? And this as condition, and the final result came out right here. The final result is a value cut bell, or I mean united with value cut step down. So this part up to this part is the resulting output file set came here. But in addition to this final file set, a bunch of intermediate file set has been created. Why? In the inference, because at first we need to find out this condition file set intersects with antecedent, right? So we get an intersected file set come here. And also we have another intersected file set come out here, right? So similarly, we have intersected file set generated during the middle of the inference. It's really troublesome, and it was use up a lot of memory. intentionally we are not going to show up this intermediate fuzzy set, right? I mean, during the inference. What we want to show is the final one, not each one of them. For now, it's okay because well, even though we don't want to show it, but remember that it do generate a point, and point take memory. If you inference later on, if we carry out the automatic inference, then we will a bunch of probably will have 100, probably 10,000 input point, and then by that case, a bunch of intermediate fuzzy has been instantiated, and also point has been allocated. You will definitely run out your memory. So back to our original philosophy. By default, our fuzzy set should not show up curve, but for constructing a fuzzy inference system, user should specify the visibility. I mean, by themselves, if they want to show the curves or the fuzzy set on the chart, they need to do that by probably turning the property on off. So right now we need to change our fuzzy set from the convention that by default, current fuzzy set by default, it generates a lot of bunch of points and also show up in the figure. So we like to set a property. By default, the property we are not going to show the curve at all. So in order not to let this intermediate fuzzy set show up during the inferencing. Okay. All right. So let us move back to our fuzzy set. Try to change the convention. All right. So start from fuzzy set. So we intended to prepare a property, right? It's a static. So right here. So we might prepare protected bool show curve, curve, show curve. By default, it's a false. And then we prepare property public capitalize show curve, and for the getter, simply return lowercase show value, and for the setter, and then we need to check if value is different from show curve. Only in this case we change it. Show curve equal value, right? And then we need to update. We need to update series. Okay, so by default, show curve does not show up, and we also need to change something there. Fuzzy set right here, right? So we blindly, at this series. Series has been instantiated. It's okay. We just don't want to instantiate a bunch of points. It will use up a lot of memory. So somehow right here, and then so we will check if show curve, right? If show curve. Only in this case we will add this series to the chart to show it up on the chart, right? If show curve. There. Well, since by default is false, right? So there is no any chance. I mean, this will be executed. So actually, we don't need to do this one. But instead, if user change this property, change this show property, we need to do this operation, right? Okay, we simply copy the whole line. So once a guy change the show curve, and then we check if show curve, then we add the series to the chart, and also we update theories. All right. But sometimes, well, the series, okay, series, okay. So we need, because this property would have been set by the user arbitrary, right? So probably it will be turn on and turn off, turn on and turn off. But in this case, if we keep turning on, then we will add multiple copy of the series to the chart. So we need to do some error proof stuff there. So let me navigate to this function. If you want to navigate to a function that belongs to a different file, we simply highlight it and right click it. We move to definition. So we came to the implementation of error file set right here. So by default, S, right? Chart area should be set to this place, and then we add this S to the series. So in order to avoid multiple add, then we need to check it. If we can check the chart.series, excuse me, the chart, not the chart area, the chart series. It's a collection. Collection always has a function called contain. Try to check whether this list or this collection contain an element or not. Right? So we simply put an S. If the series contain S, then we do not need to add it again. Otherwise it will be multiplied. But instead, if it does not contain S, then only in this case we add the S to the series. So you need to think about the logic, because right now using my extendedly changing the property, and then this series will be added multiple times. It is not okay. All right. So so far our file is set here, right? So if show curve, right? So we need to add the series to the chart and also update series. As you can remember, the update series has been called arbitrarily by some other function. So let us move to the definition right here. So since right now we have flag, right? To let the user turn on or turn off the display. So we have better add another guarding condition right here. Update series. You see, series we do add at another point, and that will use up memory. So we need to check if show curve. If not show curve, we should not do the rest of operation. Right? If not show curve, then we simply return. Okay, we're not going to add additional point to the series. That is the point we'd like to have. Okay. So right now by default it will not show up, right? As you can see, what it says right here, we will not add the series to the chart. So by default right now, nothing will show up once a guy create a file set on the universe. So new universe right here, and then we try to add a triangle function. Nothing show up right here, right? Add another one Gaussian function. Nothing show up because by default right now no point has been instantiated, and the theory does not join the chart. Okay. All right. So how should we do that? If you like to show your code, then you should do it right here. New file set. New file set, right? So we kind of create a primary file set following the specification of the user. So up to this point, target file set has been instantiated, right? Up to this point. So since by default we will show the primary file set, so in this point, you simply specify this name, target file set, turn on that property, show curve, and it turn it true, TRU, true. So let's go back to the file set. Okay, we have newly added property, right? Show curve. So if I put the breakpoint right here, so let's see what will happen. Universe, triangular file set. Okay, So we are about to change it. The new value should be true, right? But by default it's false. So show curve has been turned on, and then you see this line has been added, has been executed. So we added the series to the chart, and also let me click on F11 key, came to this place, right? So show curve, we do want to show curve, create all the point. Well, add a bunch of curve there. Alright, so that's going on. So the functionality is the same as the original one, it's okay. Okay. But right now, during the inferences, well, the intermediate 47 will not show up, but we need to pay attention to that, because right now our 47, you see, initially we did not instantiate any point. I mean, we did not invoke this update series, right? Update series to add a point, to points, the series points. But the one we specified before, the maximum degree, right? Earlier in the class, we added this property, maximum degree, right? But in the maximum degree, we kind of loop through, we kind of take advantage of the point. But right now, the point does not necessarily exist if this, for this, does not want to show up in the user interface, right? So there is no any point at all. So in this case, your maximum degree always should be a minimum value. So we need to change the code right here. We are not going to directly use the point because point does not guarantee exist. So how can we find the maximum degree? Well, it's quite simple. I mean, it's almost, well, let me check it. So maximum degree right here, right? So it will be similar to this add point. See, we need to look through the units from the lower bound to upper bound, and they use the incremental to get the membership degree right there. But for the update series, we kind of add a point. We are not going to add any point, but we still need to get the value, right? Get the membership degree of y. So it's similar. I can simply copy this stuff, and then we are no longer to use the point. So I can comment out this part, and then I set the maximum value and maximum degree. So loop through all the points and invoke this get members function value. So I have y. So I'm not doing the I'm not adding the point to points. So I simply will check if the membership degree do larger than max. So max will be set to the y, right? So once this code has been executed, we will have a maximum degree reported. It's a degree, right? It's a membership degree. Y is a degree. So I store a maximum value. I mean, so once I look through all the points, all the resolution point, and each point will have its membership degree there. So finally, what I get is a maximum degree of memory, right? But remember that, I mean, for regular for this, you need to override it, as I just mentioned for the Gaussian function early in this morning. Maximum degree just return 1. We don't bother about the looping statement, otherwise it will be very costly. Okay. All right. So up to this point, we can try it. So same operation 2, universe 1, universe 2, output universe. The first antecedent triangle find. Oops. All right. Since I have breakpoint, so remove it. Let it keep on. Gaussian, and then excuse me, I add a Gaussian. Oops. I don't know why. Maybe my mouse has problem. So antecedent 2, use Bell function 1, 2. Third one, I like to have a Gaussian. Output a Bell, and also probably triangle. Okay, triangle. And I need to specify a little bit the Bell width too much, maybe 5. And the center is okay, but the triangular move the center to maybe 24. Alright, so it's output. How about the input Gaussian right here? Let me reduce the standard deviation first. This one? I don't know. Bell. Okay, this one. The first bell, right? I don't know. No. The second bell is too large. 5. And the center probably move to 20. Alright, so I can intersection right here. And maybe option I will standard deviation make it larger. Alright, so intersection point right here, intersection point right here. And how about this Gaussian for this standard deviation? 1 intersect with the triangular this point, triangle this point. Alright, okay. So I can build the rule, two rule. First output for the set. No, not for the zeros. This is the first. And the second one, will be by default use as the inference. You need to implement this data grid, okay, by yourself. All right. So up to this point, I can inference. So let me execute up to this point. So everything is done, right? Well, let me continue it. Okay, that is the situation I like to have. Well, output is not clear, right? Output is not clear. Why? 0. Gaussian is 0. About the second rule. Oh, okay. I forget to add, display, because by default right now all the for this will be invisible. All right, the curve will be invisible. See, okay. We need to terminate it again. So let's go back to our main function after the inference, right? So we get the final output. So we need to turn on the show curve. Final output that show curve. Set it to true. We need to start all over again. Triangular, okay, 1. It's very strange. Maybe my mouse do have problem. Second universe, and I use bell. So I'm gonna Gaussian output palette triangle, and then also have bell. Okay, so let me modify a little bit. Triangle center move to 28. Left 10. Right 40. Okay, and the Gaussian 1. There, it's awful. Center curve, center 8, no, 9. Okay, the other one, center, move to 24. With slope. Okay, let me change the Gaussian to make it. So intersection point should be right here, these 2 points. And how about this Gaussian? Intersect with 0, okay, wasn't there. So I can set rule 1, 2, zeros. Oops, gosh. All right, so we need to avoid such kind of thing happen. All right, so you see, as you can see, right now the row index is -1, column index is 0. So the problem come out from row index. So in order to avoid this getting happen again, so we need to if either row index smaller than 0, return. Otherwise, once this line is executed, the exception came out. Oh shoot. Anyway, it's okay. Anyway, still alright. So what we need to make sure to try therefore triangle 1. Oh, just these two. Gaussian. Well, right here. 20. Standard deviation 1. Great. Two intersection right here. Bear function with 1. And then center A10. Level. Maybe 13. So cut one here, cut the other here. Alright, so add rule. First zeros, excuse me. Zeros. First. Inference. Remove breakpoint. Continue. Alright, so we have output fuzzy right here. This one cut united with this one cut. So we only show up the final resulting fuzzy set right here. Okay, that is our purpose. So remember that right now our convention is that by default we are not going to show up any fuzzy set. If you want to show it, you need to turn the property on, then it will show up. But again, right here, well, it's not clear for us. I mean, knowing the resulting for this array, but because each curve right now, each chart, each series is by default the chart type is line, right? There is another kind of option. You can set the chart type into area, so we will see shaded areas for this upper fuzzy set. So let us somehow extend a little bit our fuzzy set to show different kind of display. So we have show curve right there, and we like to provide public. We need to know the chart type, and I believe that should be a series, S-E-R-I-E-S, chart type, series chart type. So we call curve type CURV curve type. So it's a property again. For getter, we simply return the series dot chart type back to the caller. And how about the setter? Well, it's also straightforward. The series dot chart type equal what? Equal value set by the user anyway. So in this case, I mean, after the inferences, probably we not just show our output final. We might change final output. That should be curve type. CURV curve type. It's a enumeration. Select one area. Change the area. Okay, that's it. And we can check whether it work or not. But in this time, I simply universe, output universe. input universe. So okay, triangular, and also a Gaussian. This bell, oops, bell, Gaussian again, oops, gosh. Output is bell, and also it has a triangle there. So actually, I don't need a special two rule. Well, it's okay. I mean, let us see what's going on. I simply just special one rule, just one rule. So zeros, Bayer function, zeros. So that is the only output we would like to inference. So now I press inference. So as you can see, this is the result. Because we just have one rule, right? So output just cut for this. But right now, it's the chart type is what? Chart type is the area. So this is the area one. All right. So we just got another option anyway. Okay, I think it's pretty the content that I want to have, that we want to have for our assignment 5. And for assignment 6, the next assignment, you need to let this one. If I do not click on it, that should be scared. So you need to do that by yourself. So try to make everything complete for the assignment 5. Well, that's all.